Hello everyone, my name is Octavio Garcia. I am going to present the work Technical-economical analysis of the thermosolar plant drying different agricultural products. I am the leader of the solar drying group of the Institute of Renewable Energy of the National Autonomous University of Mexico.
In Mexico, 40% of the food is lost. These losses mainly occur in the production, storage, and distribution stages, and end up in the landfill, being another source of CO2 emissions. Also, it's common to observe open sun drying for drying some agricultural products. However, the quality and innocuity of the products are not good enough due to the exposure to different contaminants. Therefore, a hybrid thermosolar LPG plant was developed and installed in Xochitepec, Morelos, Mexico. The plant has a distributed type forced convection hybrid solar drying system, with the following components. On the top, the solar air heaters, the flat plate solar water heaters, a weather station, and inside the building, the drying chamber, the thermotank for hot water, and also all the equipment for the food processing. Also, the plant is instrumented and controlled with 52 temperature sensors, 2 water flow meters, 2 air flow meters, 5 relative humidity sensors, and 2 pyrometers. And here you can see a photo of the drying plant. The direct air heating system consists of 16 solar air heaters designed and patented by the Renewable Energy Institute. These are in an arrangement of 2 collectors in series by 8 in parallel, and it works with an axial suction fan of 3 horsepower. The drying chamber has a drying area of 52 square meters. The solar water heating system consists of 16 solar water heaters in an arrangement of 2 collectors in series by 8 in parallel. An thermal isolated storage tank of 2,500 liters and a recirculation pump of 0.5 horsepower. The indirect air heating system consists in the storage tank, and other recirculation pump of 0.5 horsepower, an air-water heat exchanger, and an LGP backup system to heat air with a heat exchanger in case of rainy days or low solar irradiance. The thermosolar plant has different operation modes. In this test, we use only 2 of them, the direct and indirect mode. A typical day of operation is that at the beginning of the day, the drying chamber is preheated with the indirect air heating system. The hot water from the storage tank heats the air that passes through the heat exchanger. After that, the direct air heating system is used during the solar day, while the solar water heating system heats the water that is stored in the thermotank. Because at the end of the solar day we are going to use again the indirect mode, so we can continue the drying process for a few more hours.
The drying chamber is a batch dry type, designed for a capacity of 500 kilograms of fresh tomato. It has a volume of 7.96 cubic meters and with a total drying area of 56.3 square meters. The inner tunnel walls, the racks, and the trays are made of food-grade stainless steel to make the process hygienic and corrosion-free. The dryer consists of 204 reels of 63 par 43 centimeters equally distributed in 3 vertical sections. The product is placed over the grill on a Teflon mesh to prevent it from sticking of the stainless steel grill.
The first figure shows the inlet and outlet solar air heaters field temperatures with an average temperature increase of 15 degrees. The second showed the global instantaneous thermal efficiencies that were between 40 and 60%, and the power of the solar air heaters was between 5 and 20 kilowatts. The direct air heating system had an effective operation time of 6.6 hours. The field of solar air heaters had an average thermal efficiency of 47%, with an average useful power of 30 kilowatts. In this slide, the first figure shows the temperatures of the field of solar water collectors, and we can see how the outlet and thermotank temperature increases through the day. On the second figure, we can see the efficiencies of the water heating system that were between 30 and 50%, and the power of the system was also between 5 and 20 kilowatts. The water heating system had an effective operation time of 6.4 hours. The field of the solar water collectors had an average thermal efficiency of 44%, and the final water temperature in the storage tank were near to 80 Celsius degrees. For the indirect modes, the effective operation time was 2.9 hours in the morning and 2.23 in the afternoon. The heat exchanger had an efficiency of 55% and 63% in the first and second indirect mode respectively, with a useful power of 7 kilowatts in the morning and 13 kilowatts in the afternoon. This figure showed the drying chamber inlet and outlet temperature and the thermotank temperature for 12 hours of continuous operation with solar technologies, which means that it worked with 100% solar fraction. Almost all the day we reached up to 40 Celsius degrees at the inlet of the drying chamber. In the first mode, we had an effective operation time of 2.9 hours, in the direct mode 6.6 hours, and at the second indirect mode 2.2 hours, giving a total operation time of 11.8 hours. With all this energy and temperatures, we could be able to remove 72 kilograms of water, giving a drying efficiency of 29%. In this slide, you can see some pictures about the process, also the drying chamber with all the product inside, and also the presentation of the final product that in the past months it has been commercialized.
In this work, the processing of pineapple, banana, apple, mango, and fig was chosen for this evaluation because they are the products that have been marketed and therefore the ones with the most drying tests available. This table shows some indicators for these products. For example, the largest amount of pulp to be dried with respect to the product in its natural state is 89% for apple, and the least is 54% for pineapple. An average maximum profit rate of 192 grams of dry product is obtained for each kilogram of fig in its natural state, while for pineapple it is only 73 grams per kilogram. Taking into account 3 millimeters slices for each product, the maximum occupancy rate of the drying area is 2.46 kilograms per square meter in the case of figs compared to a minimum of 1.61 kilograms per square meter for bananas. All the products dry in one solar day, with the exception of the fig that took 2 days. The drying tunnel has 204 trays of 63 per 43 centimeters. Considering that this is loaded to its maximum capacity with slices of 3 millimeters of fruit, it takes 191.6 kilograms of pineapple in its natural state to feed the tunnel, while only 102.2 kilograms are needed with an apple. The maximum quantity of pulp to be dried was for the fig, with 138.5 kilograms. The maximum waste of the fruit due to the peel and crowd was for pineapple, where 87.6 kilograms were wasted, while only 10.9 kilograms were wasted in apple. The total mass of dry product obtained per batch was 30.1 kilograms for figs, while the minimum was 13.9 kilograms for apple. All this with the drying tunnel at its maximum capacity. The economic analysis of the developed hybrid thermosolar LPG drying plant is necessary for assessing its commercial sustainability. The economic analysis was done by means of 2 approaches: life cycle savings and payback period methods. The detailed calculation procedure can be found in our work in applied thermal engineering, hybrid thermosolar LPG dehydrating plant installed in Xochitepec, Mexico, case study pineapple, published earlier in this year. For the economic analysis, the following considerations are made. 10 years of useful time of the plant, interest rate 10%, amortization cost 10% of the cost of the capital, cost of the total thermosolar plant with accessories $65,500, everything that is produced is sold, exchange rate 20 pesos per dollar. This table shows for each product different average indicators. 180 batches per year are considered even when in conditions in Xochitepec, Morelos, more days of drying could be carried out. In the case of the fig, only 120 batches because it takes 2 days to dry. As for the cost, the most expensive is the fig and the cheapest is the banana with 2.5 at 2 and $0.29 US per kilogram, and the sale prices of the products varies from 44 to 53 USA dollars per kilogram. This table shows economic results obtained for each product analyzed, considering annual salvage value, annualized cost, maintenance cost, and cost of the fresh product and sale price of it. According to that, the highest profit per day is obtained for bananas with 790 US dollars, and the lowest profit is for pineapple with 456 US dollars per day. With this data, we can see that the payback periods in all the cases is between 0.46 and 1.1 years. As a conclusion, it is very interesting and attractive for investors who can recover their investment in less than a year and a half. Conclusions. The average instantaneous thermal efficiency obtained in the solar water collector array was around 44%, and for the solar air heaters array was around 48%. The apple and the fig are the products that have a greatest amount of pulp, having a ratio around 88% with respect to their natural state, and with this, more pulp could be dried in these products. The product with the highest profit is banana due to the low cost of the fresh material and its average yield of the use of dry weight with respect to the weight in its natural state. Recovery of the investment in this case is in 0.46 years. The fig presents a long payback period, around 1.1 years, because it takes 2 days in drying, and this affects the economical results. A thermosolar plant was designed, built, and evaluated in Xochitepec, Morelos for drying agricultural products. According to the results obtained, different types of products can be dried, which translates into significant fuel and economic savings and environmental benefits. This plant was developed as a result of the project development of low and medium temperature solar collectors for process heat in industry, awarded by the PRODETS Award. Thank you very much.